Okay, so our next section is vector equations of a line. Here is the formula. It's R, where there is a point plus a parameter lambda times the directional vector B. Super complicated sounding, but not actually too bad. When you break that down into pieces, when you think about what a vector looked like, this parametric form is just taking the components and adding them together. Like it's just splitting up the formula above it. And then the third formula for Cartesian equations is where you solve each equation for lambda and set them equal to each other. Again, not too bad. But you'll notice that the L, M, and N are the directional vectors in the parametric form of the equation of the line, and they're also the directional vectors in the bottom one. So make sure that you connect that the denominators of the Cartesian equation are the directional vectors. Not something you need to know right this second, but it will come up. Okay, a normal vector is perpendicular or orthogonal to any vector on the line. So if you have n times n with the dot product of, or the scalar product of a, p, or any vector, if it's equal to 0, then it is perpendicular or orthogonal. So you'll have a lot of questions that say, find the perpendicular. Are these perpendicular? And you have to prove it. So we'll talk a little bit more about those as well. Normals and equations are not unique until you incorporate that specific point with them. So let's look at this first example. They want us to find the equation of the line in slope-intercept form passing through the point -3, 4 with the directional vector of 2, -1, or sorry, 2i minus j. Okay, so when I come up with that, I have my formula. So I have P is equal to A plus lambda D. So what I end up with here is that I have XY is equal to my coordinate points, -3, 4, plus lambda, and then my directional vector would be 2, -1. Once I have that, I'm just going to split these into two pieces. I have that X is equal to -3 plus 2 lambda, and Y is equal to 4 minus lambda. What I can do now is figure out what both of these lambdas are. So I end up solving for lambda, and I get X plus 3 over 2 is equal to Y minus 4 over -1. And now I'm just going to solve for Y. This is just algebra. I really hope by now you can do that. You cross multiply, you solve for Y. You should end up getting Y is equal to -1/2 X plus 5/2. Okay, so that's the first one. And then the second one is a normal vector, 3i plus 5j. So what that tells me is if it passes through the normal, I know that n dot p minus a is going to be equal to 0. Now look back at your notes for the properties of a dot product, and then I can say that n dot p is equal to n dot a. I can distribute the n dot and then move the -1 to the other side to make it positive. So I have this. So now I get to just set it up. So the normal vector is 3, 5. Dot our point would be xy is equal to 3, 5 dot -3, 4, which is our point that's given to us. I will one day stop trying to write that as a fraction. Okay, so now that I have these components, I have 3x plus 5y is equal to -9 plus 20, which when I solve that for y, I get y equals -3/5 x plus 11/5. Awesome. Okay, so problems may ask you to use multiple forms. So this first one wants you to find the point of intersection. So the first thing I'm going to do is just rewrite the first one in more of a parametric form. So I have x, y equals 2, -5 plus lambda, -1, 3. And then I can condense that even further to say that x equals 2 minus lambda and y equals -5 plus 3 lambda. Okay, from here, I am going to take the places where I have my x and my y and plug it into this second form. So now I have 2 minus lambda instead of the x plus 2 over 3 is equal to 1 minus, and then instead of y, I have -5 plus 3 lambda. Okay, from here, I am just going to solve, combine like terms. You should end up getting that lambda is equal to 7/4. Once you have this answer, you're going to plug it back in up here. And you should get the points 1/4, 1/4, right? Moving on from there. Remember that parallel lines have the same directional vector and perpendicular ones have a directional vector such that their dot product is 0. We just talked about that a little bit, but just make sure you remember that parallel has the same directional vector. Okay, so we're going to look at both of these and make sure we've got it down. So for part A, we will do the parallels. So we have A, we have our point would be 1 plus lambda I plus lambda minus 2j. Okay, from here, I can rewrite this. What I'm going to do is multiply across and then combine my lambda terms so that I have a directional vector. I know that sounds really bizarre, but I'm basically distributing the I and the j and then grouping like terms. So I have 1 times I, and then you would have plus lambda I plus lambda j minus 2j. So now I have that. If I pull out the lambda from that lambda grouping that I just said, I would have just I plus j. Okay, so now I know that this here is my directional vector. So I can say that D is equal to I plus j. So now I can say that there is a parallel line through the point. I just use the point -4, 1. So I can say that R is equal to -4I plus j. Now I'm going to use just a different symbol other than lambda. We'll use mu times I plus j. So that's my parallel line. And now to do perpendicular, I know that The directional vector we came up with was I plus j. So that means that the normal would be I minus j. So then I come up with my formula where I have r is equal to -4i plus j plus lambda times I minus j. Just my normal directional vector. Okay. In a 3D space, two lines can be parallel, intersect at one common point, or be skew. To be skew means that they are not parallel and they do not intersect at a common point. So now I have to prove or show that these are skew. So in order to show that they are skew, I first have to show that they are not parallel. The definition of parallel means they have the same directional vector. So I just have to figure out what the directional vectors are of each of them. So this first one in red, its directional vector would be 3, 2, 1, just the denominators right there. And the second one would be -2, 3, 4. These two things are not the same. Since they are not the same, I know it's not parallel. Now I need to prove that they don't intersect. In order to show that they don't intersect, I have to show that their x, y, and z are not the same. So this is going back to that idea of proof by contradiction. If I want to show that they don't intersect, first I have to try to make them intersect. So I have that in the first one, x is equal to 1 plus 3 lambda. Y is equal to -2 plus 2 lambda. And z is just equal to lambda. All I did was set each of these equal to lambda and then solve for x or y or z. So then the second one, when I solve all of those, I have -3 minus 2 mu, 3 mu, and 2 plus 4 mu. This last one here has given me now something to plug in up here. So now if I break each of these down, I end up getting I'll do a couple in between steps, I guess. 6 plus 12 mu plus 2 mu equals -4. 4 plus 8 mu minus 3 mu equals 2, and lambda equals 2 plus 4 mu. Math happens. You should get here that mu is equal to -5/7. And here you get that mu is equal to -2/5. Now these two things are not the same. So we have reached a contradiction. Which means there is no intersection. Which means, therefore, the line must be skew. I would write out all of those words, but I just said them, so. Okay, so those are your notes. There is a worksheet to practice. Go ahead and get started.